Hello friends, today we will continue. Before that, let me tell you once again that welcome to this technical session on design of rapid gravity sand filter unit. We are continuing, in fact. So in the design of rapid gravity sand filtration system, you see that there are a few components. I have kept the diagram still now because just to sort of see while designing this one, so that we can explain also, right? So first we showed that how to design or find out the minimum depth of sand, then this sand, then the layer of gravel, what should be the depth of that, then the under drainage system, and the outlet also we are not designing because this is outside the filter. So only the filter, the internal parts also here we are designing, and next we will take up the design that of wash water collection system. I have explained in my earlier discussion on the design considerations also, including that wash water collection system. And as I told that the under drainage system, especially the central manifold and the lateral system, if it is in this direction, suppose that is the laterals are coming this way and there is a sort of this one, that means it is like that, right? So the fingers, if you see that fingers, so this actually are the laterals, this side and this sides, and the in between manifold also. So manifold, as I have stated earlier also while discussing the design considerations and components also, that manifold may be placed at the middle between the laterals, the series of laterals also, battery of laterals, or it may be placed at the end also, right? All the laterals are connected like that. But when the filter, length is length or width is rather large or so, in that case high, in that case actually the L by D ratio, that is length to diameter ratio, I think I discussed this one in design considerations, that should not exceed 60. I think I discussed this one earlier. So because from structural strength point of view, L by 60, the ratio of length to diameter of the laterals should not exceed 60, because it would be a long kind of component, structural component, and the slenderness ratio, that is defined by length of the laterals and the diameter also, right? So this should not be too long or so, should not be too high, L by D ratio, it should not exceed 60 or so. So that is why why I am saying this, because when the laterals should be too long and the manifold at the end also, then in that case there is a possibility that lateral length will be high enough to exceed that ratio L by D, that is 60 or so. So to avoid that, first thing we should be careful about that, because otherwise structurally the laterals will be weak or so. In that case the laterals may be broken, may be collapsed, structurally failed or so, structural failure or so, and leading to that entire the under drainage system to be non-operating and non-functional also. So that is why we have placed it at the middle, the manifold system. So what I was trying to say, that laterals these are this direction, then this one that the wash water collection system, it is better to put like that, okay? But one thing you should remember, that let me show this, that when this this will be, here as you see, if I draw it, just the section. So what would happen actually, as you see here, that is the entire, this one is coming throughout the length or the width also. If this side is the width, say, so this side width and falling, and here the water supply, that inlet from the preceding unit also, the entry will be at the upper level also, and this one at the bottom level also. That means the wastewater which is discharged, the wash water also, after this backwashing also. So this actually will be collected in this line, so that must be put on the bottom also, while the water supply, this water supply or the from the preceding unit, the entry of water into the filtration system, that entry level should be much higher than this one, so that cross contamination should not take place also, right? So this is one arrangement, but here we have placed at the middle also. That means here you see that this is the gullet also, right? This is the gullet. If you see the section, then this gullet is like this, right? So this one is coming like that, the laterals also, like that. So it is coming this side also, like that. So this will be collected this way, right? And while the under drainage system may be like that. That means this is actually this side the laterals, and both side laterals, this one under drainage system, and then this actually will be discharged into that the main manifold system also. So then entire the hydraulics, the distribution pattern also, that would be rather more efficient for the operation of the filter. Coming back to this, the design of wash water collection system also, wash water collection system. Now this is something like that. Okay, I'll draw it, the sketch, in a more clear also, more clearly also, design of that this is wash water collection system, right? So here actually what will be there, first thing is that we have to find out that what would be the total backwash water which is being collected by the filter, each and individual individual the filter bed also. So first we will see that how to calculate this one. Now here you see that compute the dimension of wash water trough, that is the compute the dimension of wash water trough. Trough means these troughs. This is gullet, this is troughs. Okay. Now assuming that the wash water rate, which earlier we have discussed, standard rate what we take at say 36 meter cube per hour per meter square also. This is a backwash rate what usually we follow. The range is given in the CPHEEO manual, and also I have discussed earlier the range. From that range actually we have taken the typical value, that is 36 meter cube per hour per meter square or meter per hour, same, right? So at that rate actually the wash water discharge or collection also you can say, discharge through the bed, that is where discharge, collection, if you use this, then the collection into the troughs and finally into the gullet also. For one filter bed, one and each, you can say, individual filter bed, one filter bed, or individual, you can write more to be more clear, individual, right? So this should be 36 into each. The bed has got a, we calculated earlier, I am not repeating this one, that is the, 26.33 meters cube per hour or so, right? So that is actually 36 meter cube per hour into meter square, that is, this is actually in meter square area, because we provided for 2 being minimum, here we have provided minimum of 2 filter, and each one having a plan area of 26.33, making the total to be 52.6 or so, as I remember. So that actually came from the calculations at the beginning or so, that what is the plan area that we have already calculated. So this is the meter square and this is the meter cube per hour per meter square, right? So ultimately this will be the unit if you multiply this. So this will be, that 9, 4, say 8 meter cube per hour, okay, meter cube per hour. To that, sometimes what we do, if we use that water, from clearing the surface, I explained that, right? That when you, suppose this is a filter box, so at the upper end we have provided the jet also, sometimes to break the clay patch also, or mud ball formed on the surface of the filter bed also, to break that one, or to sort of clear the clay patch which otherwise is not being cleared also, then in that case sometimes we use a surface wash also. So in that case actually we should add the surface wash water also, right, to the backwash water also. So in this case we are not, using, or we are not adding, because we are not using the surface water also. But if you go for the surface wash also, then in that case you should add this, right? So if we assume, and we also explain that suppose this is a trough, a single trough, say, right, and another wash water trough. These are all wash water troughs, right? This one, and maybe others. Now these are horizontally placed, as you see here, horizontal. Okay, so this troughs actually, this, if we make like that half of that actually, that will be collected from this area for each, this one, right? If we use a shade also, then that means actually that this area and this area, right? So that actually will be, collected by one trough also, and that distance, normally you see that distance, that 0.6 to 0.6 to 1 meter. That means the maximum travel of dirty darts materials while backwashing, the dirt materials, maximum travel to get to get cleared into the trough also, it could travel, maximum travel is 0.6 to 1 meter or so, right? So accordingly we will design. So suppose we are taking the average value, that is 0.8 meter. That means from this side, suppose this is the wash water trough we are designing. Similar design or same design will be for other troughs also. Now here 0.8 and this side 0.8. So this is the 0.8 or so. So 0.8 plus 0.8. We are not considering that this is the width because this is very small, you know, right? So 1.6 meter actually, right? So that actually will be the spacing. So this spacing here, similarly here also you see that for this one, so this is the 0.8, right, meter. This is also 0.8 meter. So this makes this out to out, say 0.8 plus 0.8 meter, that is 1.6 meter. So that is the, here we are taking the spacing of the wash water trough. If it is more than that, maximum 2 it could go, but to be on the safer side, we have taken the intermediate value of say 1.6. Otherwise, if it is too long, then by the time the backwash is done, actually by that time the dirt materials may not be able to, you know, may not be able to reach the wash water trough and get clear. So that possibility is there. So to avoid that, likelihood of that, the dirt materials to be unable to reach here, we have taken 0.8 plus 0.8, that is 1.6, the spacing of the wash water trough. Okay, so you see that here we have, see, this is the, you know, that total, this one, if we take 4.5 meter, this is the width of that, and this side the length is 5.8 meter or so, right? So the number of troughs could be calculated from this, right? Number of troughs I'm just erasing this one, right, because it is already captured. You can find out that number of troughs for wash water collection also. So I think you understand that how to get the number, how to get, that is 4.5 meters, because this way we have placed this one, so that all will collect this one here this way, and will will discharge this into the gutter also, which is placed this way, right? So this will be placed like that. Okay, so this will be discharged like that. Another here, suppose, right? So this will be discharged here. This is the plan of the gullet also. Clear? This one. So this will be ultimately discharging into this gullet like chamber also. So if we have provided like that, then in that case the number of troughs will be 4.5 meter divided by 1.6 is the spacing. Well, the spacing we have considered here of the wash water troughs also. So this will be more or less, say, it will be on the little higher side. So this will be 3, say 3 numbers. 3 makes that 4.8 meter, but 4.8 meter is not that. So this has to be compromised. That means this will be more or less, say 1.5 or so, 1.5 or so, right? So this will be 1.5 to make it 3 also, if we provide 3. So and also I have stated that the end, this one, right, there should not be any wash water trough just at the end, that means with the wall the inner wall, inside wall of the filter as one of the sides also, right? That should be avoided. That should be, otherwise this should be the wasted also. So little below that one. That means here it would be, say, if we provide this one here, so this actually will be 0.8 meter away from the wall. This side also 0.8 meter away from that. So as you see that here, suppose this is another wall here, so this will be 0.8 meter away from the wall, and we have kept, and here also we have kept that the third one here, right? If I give little bit of more visibility also, so 0.8 meter, 0.8 meter, so 1.6, this is 1.6, 1.6, so making that this is 4.5 or so, more or less. Clear this one? So I mean that way we have to, I mean here 1.5, so this is 1.5, 0.75, 1.5, 1.5 and 0.75, if we make these three or so. Okay. Now the discharge per unit drop, so find out the discharge of dirty or backwash water per unit drop, right? You can find this one. I think you understand this. Now this will be, discharge will be total discharge, that is discharge per unit drop, that would be, we have calculated that this one 9447 or 948 we considered meter cube per hour, right? And if we make it meter cube per second or so, dividing by 60 or so, 60 by 60 into 60, that is 3600. So 948 by 3600, that is second per hour, meter cube per hour. So this actually will give you 0.26. You may check this calculations, okay? There may be slight, deviation also, maybe, because of decimal that is there. You can check this. So as it has come here, the 0.2633 meter cube per second, that is this one here, divided by 3. So total one that was calculated like that. So this divided by 3. So this would be, I am putting in the bracket, so the total discharge and discharge per backwash water, backwash trap, sorry, here. Discharge or backwash per unit drop. Discharge of backwash water. No, it was okay. Discharge of backwash water per unit drop. This will be just, I have written because it is there. It is making a sort of, obstruction or so. That is why per unit drop. So this will be 0.2633 meter cube per second divided by 3 number of drops. That is there. So per drop, the collection will be, the discharge or collection per unit drop will be 0.0878 meter cube per second, or you can say very close to 0.88 or so, right? So 3 are there. So total filter this backwash water to be collected by 3 or to be discharged into 3 wash water trough or so, as we here we have erased this one. So 3. So this actually will be there. And if we use sort of a backwash this trough, this is, I explained this, that the backwash, or the section of that, right, this backwash lines. So this would be So this is the going like that. So it will be collected like that. So here if we use that the width as 0.4 meter. So this is, I have shown it three-dimensionally, but if you make it like this, the water is this. Okay. This is like that. So this is W, say, this is W, and this is, or B, say, and this is the H. I earlier explained this, all this, right? So, I mean that the side spillway also, so that way, or I mean level invert, the collection, how it is there, in that case actually this will be falling into this gullet also, so this will be the profile of that, right? And if it is level also, right? And here we are considering this level. If it is level, then at the uppermost uppermost point, the discharge equations I gave. I explained that at the upper end also the water depth will be, could be calculated this way, that is Q 1.376 B H 5/2, right? 5/2. This I have explained, so I am not going to explain it once again, right? I am erasing this one, but because this horizontal placement I have made it clear. I think that you have understood this. Why the spacing is 1.6 we have considered, and the collection, how it is divided into three or so, the three troughs we have provided. So all these, supposing that you have understood also. Now the section also, this one, and same will be for the others also. One wash water trough system, how this one here, this if long this one wise, so this actually will be falling like that. Okay, so water will be like this, it will be falling into the gullet, okay, after traversing this distance. So the given length also, so it will be in the gullet, it will be discharge also, right? Now this is the equation already I have explained, that what is what. Q is the discharge rate also, B is the width of this one, and the shape, it may be like this, suppose. Accordingly hydraulics will be little different also, right? Or it may be U shaped. In that case actually this will be like this, all will be like this, right? So these are the common configurations, or I mean the shape of the wash water trough line. So here we are using this one. You may use this one, very common, all three are common, you can say. And corresponding equations here we are giving the depth. In this case the depth will be, H will be this, width will be this. In this case the depth will be from the inner, this invert to this H, and U is this, H for U, B is this, like that. So if we put this value now, because per trough the discharge is 0.88 meter cube per second, so this would be say 0.88 per unit trough, remember. And three wash water trough we have provided here with a spacing of outer, this spacing out to out, this one means outer wall of another, one to the outer wall another, that means this spacing, right? So this 1.6 meter or so, and this actually will be 1.376 into 0.4 into H 5/2, and this will give you, H means this liquid depth, This is the liquid depth, remember. So this is 0.294 meter, right? Say 3 meter, 0.3 meter, after rounding off. Okay, and if we provide a freeboard of 0.1 meter, that means freeboard means here, this freeboard, that is freeboard of 0.1 meter. So 0.1 meter. So overall depth comes as 0.4. So providing a freeboard of this, the overall depth of trough happens to be 0.3 plus 0.1, that is 0.4 meter. That means this will be 0.4 meter. So this will be 0.4 by 0.4. Okay. Here we have directly assumed that before calculation of this, finding out the liquid depth also inside the wash water trough, we have provided 0.4 or so. If you do not get any clue or no experience also, in that case B and H you can take same also initially. Okay, B and H, and accordingly you can calculate this one. So this actually will be and depth is 0.4 meter. So depth 0.4. So the trough size, the size of each trough, right? So that will be 0.4 meter depth by 0.4 meter, you know, that B. So this will be this size of that. So it is now the dimensioning of that that is clear, including the water level in that, and that actually water level has been, you know, determined based on the equation, this equation for when the depth will be at the uppermost end also, right? Because this actually will be the profile, backwater curve also, like that. Before falling into that, this would be a sort of critical depth or critical depth, say. So here this will be through critical depth, it will fall into this one, free falling, rectangular free falling, this one channel, rectangular channel with the flow of that, and which is freely falling into the gullet or so. So that would be the depth here at the uppermost point. And that depth we will consider enter this one. We cannot reduce this one, right? Because structurally it will be difficult. That changing the depth of the trough as it goes to the towards this gullet. So this is this. I think it is clear to all of you. So it is already captured. So I am not repeating this one, because if any trouble in understanding this, you can talk to me in or over Google Meet or so, as I have been telling every time, right? Or personal communication also you can use for a by a registered participant of this course. They can communicate through personal communication, means through mail also. Okay, and the total depth of the filter box, step 5 say, this is very simple then. The depth, total depth of filter, each filter box. So that will be, this will be the under drainage depth, that is we have provided a manifold depth of this, that was 80 or 800 millimeter, that means 0.8 meter or so. The gravel depth is this 0.5 meter, sand depth 0.6 minimum we had to provide, It was coming 0.46, but we this being minimum, we have provided minimum. Then standing water on the this one 1.1 to 1.5 meter, we have taken 1.2 meter or so, plus 0.3 meter. This is the standing water depth. This is the freeboard. This is the sand depth, this is the gravel depth, and this is the under depth. So this makes the total depth as this, right, up to this bottom of the filter to the floor. So this actually will be, say, 0.3, so 1.5, 2.1, 2.6. So this is, so 3.40 meter. That is the overall depth of the filter box, right? And next, actually, step 6 or the last step, say here. So that is the determination of initial head loss. And we discussed this, how to find out the initial head loss, that means during that, immediately after backwashing, when the filtration cycle has started, once again resumed after immediately after the backwashing, then this actually initial head loss should not exceed 0.3 meter or so. It should not exceed 0.3 meter or so. So this initial head loss is calculated, right, based on the, calculated by Karman-Cousins equation, sometimes Cousins equation also as it is called, but Karman-Cousins constant we have used, that is a K or so. And while this formula has been given earlier, the application of the formula that we will discuss in my on filtration design of filter unit. Next video we will discuss that along with the some operational features also, and with that we will conclude. In our next this video session, lecture session, we will conclude the design of filter system along with little bit of operational features also. Thank you so much for your patient viewing also. Okay, thank you.